The Hoover Dam, a monumental achievement, harnessing the immense power of the Colorado River.
Its function begins with the vast reservoir, Lake Mead, providing the necessary head of water. Water is drawn into the dam's system through massive, structurally sound intake towers. These gates control the initial, critical flow of water into the deepest parts of the dam's infrastructure.
This process sets the stage for hydropower generation, transforming potential energy into kinetic force.
The water then enters the long, immense pressure conduits, engineered for high velocity. These large pipes, known as penstocks, guide the colossal volume of water down toward the power plant.
The water flow must be meticulously controlled and accelerated for maximum efficiency at the generation stage.
At the base of the dam sits the power plant, the heart of the electricity generation process.
Deep within the plant are the Francis-type turbines, designed to capture the immense energy of the falling water. High-pressure water is directed onto the turbine blades, where its kinetic energy is immediately transferred.
Impact generates a massive torque, causing the heavy turbine to spin rapidly on its vertical axis.
This rotational force is mechanically transmitted upward through a durable vertical shaft. The shaft is directly linked to the generator, where mechanical motion is converted into electrical power. Inside the generator, the massive rotor, fitted with powerful electromagnets, begins its rotation. As the rotor spins within the stationary copper coils, the principle of electromagnetic induction takes hold. This movement creates a powerful, sustained electrical current, the birth of the generated power. The used water is discharged from the turbine into the tail race, ready to continue its journey down the Colorado River.
This entire process, from intake to outflow, is known as the hydropower cycle, reliable and renewable.
The generated electricity must now be prepared for long-distance transmission across the Southwest grid. The power is fed into transformers, which step up the voltage for efficient long-distance travel. From here, the high-voltage power travels along the transmission lines to distant cities and municipalities. Mechanical rotation has been successfully converted and distributed as clean electrical power. This single dam generates enough electricity to reliably serve over 1 million people across the region.
Beyond power, the dam is a critical water management tool, ensuring stable river flow. The spillways provide vital flood control, protecting communities and infrastructure downstream.
It also supplies essential water for irrigation, sustaining agriculture in the arid Southwest.
The Hoover Dam is an engineering marvel, a testament to human innovation and scale.
Its colossal size and intricate systems transform the challenging resources of the Colorado River.
To grasp the scale, the penstock pipes are physically large enough to accommodate a full-size semi-truck.
The Francis turbine is specifically chosen for its high efficiency under the dam's substantial water pressure.
The journey of a single drop of water demonstrates the entire energy conversion process in miniature.
Precision engineering ensures the seamless transfer of mechanical energy from the turbine to the generator. The efficiency of the generator relies on the constant, high-speed movement of the electromagnets.
Transformers manage enormous power loads, requiring robust systems for heat dissipation and cooling.
The switchyard acts as the distribution hub, channeling the high-voltage power to its final destinations.
Within the dam structure, a complex network of tunnels allows for constant monitoring and maintenance access.
The reservoir's level is continuously monitored, balancing power needs with downstream water demands.
The flow can be halted at the intake, allowing for controlled shutdowns or maintenance procedures.
The curvature of the Francis blades is essential, maximizing the kinetic energy capture from the high-velocity flow. Multiple generating units operate in unison, allowing the dam to meet varying demands for electricity.
Stationary stator coils are crafted from high-grade copper, optimized for conducting the resulting electrical current. The mechanical connection between the shaft and the rotor must be extremely secure to handle the rotational forces.
After generating power, the water continues its essential role, supplying the lower Colorado River basin.
We use a specific color coding to clearly delineate the different physical and energetic elements. The shear drop, or head of the water, is what provides the massive pressure for the turbines.
The dam's arch-gravity design distributes the immense water pressure efficiently onto the canyon walls.
The penstocks are meticulously fitted into the concrete structure to withstand extreme internal water pressure. The entire operation is monitored and controlled by engineers, ensuring peak performance and safety. Massive valves are installed to instantly stop the water flow to any individual turbine unit for safety or maintenance. The rotor's electromagnets are energized to create the powerful magnetic fields necessary for power generation. High current flow through the copper coils generates heat, which must be efficiently managed by the cooling systems. Specialized cooling systems, often using oil as a medium, prevent overheating in the high-voltage transformers.
The dam operates around the clock, providing baseload power to maintain stability in the southwest grid.
The dam transformed the highly variable flow of the Colorado River into a predictable, managed resource.
The intake towers remain the silent sentinels, managing the critical entry point of the water supply.
Robust bearing assemblies ensure the smooth, vertical rotation of the multi-ton shaft and rotor. The pressure increase is calculated precisely based on the significant vertical drop the water undertakes.
This vast concrete structure is designed to withstand a force equivalent to millions of tons of water pressure.
Generators produce alternating current, synchronized to the specific frequency required by the power grid.
Each turbine runner is a massive piece of cast metal, requiring specialized machinery for installation and maintenance.
The transformation process is key to minimizing energy loss during the hundreds of miles of transmission.
The dam was built in interlocking blocks, with cooling systems initially used to manage the concrete curing process.
Lake Mead, the reservoir, holds back the largest volume of water in the United States when at full capacity.
Air cooling systems are used in tandem with other methods to regulate the generator's operating temperature.
The massive transmission towers must securely hold the high-voltage lines, insulated from the ground. The electricity generated here powers homes, industries, and critical infrastructure across the region.
The penstock's steel lining is incredibly thick, ensuring structural integrity against the tremendous force of the water. Hydropower is a highly efficient energy source, converting kinetic energy with minimal loss.
The speed of the generator is precisely regulated to ensure the stability of the electrical output. Regular inspection of the penstocks is vital to ensure no buildup or damage compromises the water flow.
The sheer scale of the engineering effort is evident in the harmonious blend of concrete and natural rock. Various outlets and valves allow for controlled releases of water for downstream ecological and resource needs.
Located on the border of Nevada and Arizona, the dam serves as a shared, vital resource for the entire Southwest. The design of the power plant prioritized both robust functionality and long-term durability.
The dam's primary structural purpose is to resist the colossal hydrostatic force of the stored water. Effective sealing is necessary to prevent leakage where the turbine meets the foundation of the powerhouse.
The continuous flow of power guarantees that essential infrastructure across multiple states remains operational. From the massive intake towers to the high-voltage wires, every component is part of one integrated system. The Hoover Dam, a timeless engineering marvel, a provider of power and a master of the Colorado River's flow.